We're going to continue to look at cylindrical geometry, and in this case, we are looking at an infinite line charge and a conducting shell surrounding the infinite line charge. So our infinite line charge first. So that's the blue that we have down here. So these blue charges lined up represent our infinite line charge, and we are told that the blue infinite line charge has 8 microcoulombs per meter. So if we do 1, 2, 3, 4, 5, 6, 7, 8. So if each of those charges represented 1 microcoulomb, and this was our 1 meter distance here, we would have 8 microcoulombs per meter. Now, we are told that surrounding that infinite line charge is a conducting shell with a radius, inner radius A, outer radius B. So if we look at our inner radius A, outer radius B, it's a cylindrical shell, so you can think of it as like a pipe, where we have a thickness to this metal pipe, and we are told that that pipe or that shell has a charge of plus 2 microcoulombs per meter. Now, the way to understand that is to think of any 1 meter section of the pipe. So if we consider a 1 meter section of the pipe, 1 meter would correspond to plus 2 microcoulombs of charge. So for every meter, we get plus 2 microcoulombs. Now, to go from r equals 0 to r equals infinity, we're going to start and then work our way out and look at the different regions of interest. Our first region of interest is to go from little r equals 0 to r equals a. So our Q enclosed is only the infinite line charge at the center, the plus 8 microcoulombs. So please review our last page of notes, our derivation for the electric field outside of an infinite line charge, because in Roman numeral 1 section, so our Gaussian surface, Roman numeral 1 will be identical to just the infinite line charge, because that's all that is enclosed. Now, how about from A to B? Now, from A to B, I put my Gaussian surface anywhere in between, but this becomes very easy, because as it says here, the electric field inside of conductors is 0. So that means Q enclosed equals 0. And that boils down for us now to the fact that lambda enclosed must also be 0. So now lambda enclosed has to equal 0. And what does that mean about the charge on the surfaces? So we've done this before with the spherical conductor. We know that we have a plus 8 microcoulombs, right? Charge at the center. We know I need 0 Q enclosed inside of the conductor, so that means that I must have negative 8 microcoulombs on the inner side of the pipe or the shell. Since my total is plus 2, that means on the outer portion of the shell, I have to have plus 10 microcoulombs on the outer portion to allow my total to still equal the plus 2 microcoulombs per meter that we were given. So now we have the Roman numeral 1 and Roman numeral 2 sections done, so that's our graph down here. So those, I think, were the easier parts to consider. And now we just need to consider our Roman numeral 3 section, which will be from r equals b out to infinity. So we're going to put a Gaussian surface somewhere in up here, and let's see what that solution looks like. Well, that also is not a terribly difficult Gauss's law derivation, because we know Q enclosed equals all of it. So that means we have a plus 8 microcoulomb line charge at the center, plus 2 microcoulomb charge on the shell, so we have a plus 10 microcoulomb charge overall. That means the electric field from B out to infinity is going to still be represented by our hyperbolic 1 on 2 pi epsilon naught lambda on r, where the lambda enclosed now equals the plus 10 microcoulombs. So my extension question down here we have already answered. That's the lambdas on the inner surface, the outer surface. That's our plus or minus 8 and plus 10 that we just talked about. And the final thing that I want to touch on is over here on our graph, because in this problem we don't really know whether our 1 on r dependence, so our equation down here, whether this equation corresponds to the top graph or to the bottom. So please make sure you get this into your notes. Since we don't know the thickness of the shell, if the shell was very thick, so this r distance was really big, that would cause the graph to be smaller as we go out here, and that plus 2 microcoulombs, right, that we picked up wouldn't outweigh that distance in r. So really it's a balance between the plus 2 that we picked up and the 1 on r distance of the shell. If the shell were thin, then that would correspond more to the graph going up higher than we would normally think based on the thinness of the shell. So please make sure you get that into your notes. Hopefully all of this makes sense based on our understanding of the infinite line charge, and we will continue on.